Hello everyone! For today's discussion here in Advanced Engineering Mathematics for Civil Engineers, we are going to discuss the first part of Laplace transform. So for this lesson, students must be able to transform time domain functions to frequency domain functions. So let's start our discussion. Okay, so let's talk about Laplace transform. In mathematics, the Laplace transform is an integral transform named after its inventor, Pierre-Simon Laplace. Okay, so it transforms a function of a time variable t that is in seconds to a function of a frequency variable s that is in per second. The transform has many applications in science and engineering. Okay, so for this topic, the given function here is a function wherein the variable is t. Okay, so that is time, no? And since that is time, the unit for that is second. So what we're going to do with this function, we are going to transform this, okay, into a function, okay, wherein the variable is variable s. And that variable s is a frequency variable. And since it is frequency, the unit for that is per second. Okay, so that function in a frequency variable, that is the Laplace transform. Okay, so we use Laplace transform to convert equations having complex differential equations to relatively simple equations having polynomials. So it will be much simpler, okay, if we convert functions with variable t to functions with variable s. Okay, so since equations having polynomials are easier to solve, we employ Laplace transform to make calculations easier. Okay, so let's proceed now to the applications of Laplace transform in engineering. So Laplace transform has several applications in almost all engineering disciplines. So the first one is for system modeling. Laplace transform is used to simplify calculations in system modeling where large differential equations are used. Okay, the second one is for analysis of electrical circuits. In electrical circuits, a Laplace transform is used for the analysis of linear time invariant systems. And the third one is for analysis of electronic circuits. Laplace transform is widely used by electronics engineers to quickly solve differential equations occurring in the analysis of electronic circuits. So the fourth application is for digital signal processing. One cannot imagine solving DSP or digital signal processing problems without employing Laplace transform. So the fifth application is for nuclear physics. In order to get the true form of radioactive decay, a Laplace transform is used. It makes studying analytic part of nuclear physics possible. And the last one is for process controls. Laplace transforms are critical for process controls. It helps analyze the variables, which when altered, produces desired manipulations in the result. For example, while study heat experiments, Laplace transform is used to find out to what extent the given input can be altered by changing temperature. Hence, one can alter temperature to get desired output for a while. This is an efficient and easier way to control processes that are guided by differential equations. So, to simply put these applications, no, so Laplace transform will be useful, okay, since it will be much easier, okay, to compute functions with variable s than functions with variable t. So we will be able to see that, okay, in our examples for this. So this is the notation of Laplace transform. If f of t, or the function given wherein the variable is t, okay, is a function defined for all t is greater than or equal to 0, meaning to say for time, no, there is no negative time. No, so its Laplace transform is the integral of f of t times e raised to negative st from times equal to 0 to infinity. So it is a function of s, say f of s. So f of s is the Laplace transform. Okay, and it is denoted, it can also be denoted by this symbol. So this symbol is Laplace transform of f of t. So f of t is the given time domain function. Thus, okay, the Laplace transform is equal to the Laplace transform of the given f of t, and that will be equal to integral of e raised to negative st times f of t, which is the given time domain function dt from 0 to infinity. So we will use this formula in solving for a Laplace transform of a given time domain function. Okay, so for this, f of s is the frequency domain function called the Laplace transform of the time domain function f of t. So again, f of s, this is the frequency domain function, and f of t, this is the given here. So this is the time domain function. So we are going to convert or transform this time domain function to frequency domain functions. And to do that, we are going to use this formula. Okay, so it is very important for this topic, okay, that we still remember what we have learned from our calculus courses, from differential calculus, integral calculus, and differential equations, because we are going to use them to this topic. Okay, so let us first recall, no, some basic differentiation rules that we learned from your differential calculus. So we are going to use these rules, no, for solving Laplace transform. Okay, so you have to recall power rule. So for power rule, the derivative of x raised to n will just be n times x raised to n minus 1. Okay, that is our power rule. Now for chain rule, the derivative of a function, okay, wherein in that function, inside that function, there is a function. Okay, so we will use chain rule for that. Okay, that the derivative of f of g of x here, okay, it will multiply further by the derivative of the function inside here. Okay, so that is for chain rule. Okay, you have also to recall our product rule for differentiation. So if we have product uv, so that will just be u dv plus v du. So for quotient rule, if we have here derivative of u over v, that will just be v du minus u dv over v squared. Okay, and also for derivative of sine x, that is just equal to cosine x, and for the derivative of cosine x, that will be negative sine x. So it will be useful here, class. So you have to recall this differentiation rules. Also, from your integral calculus, let us recall some basic integration rules that we can apply in solving for Laplace transform. Okay, so we have here integral of k dx, wherein k here is constant. So the rule here is we can take out, no, outside the integral symbol this constant. Okay, also for power rule of integration, let's say we're going to integrate x raised to n, that will just be x raised to n plus 1 over n plus 1 plus c. Okay, also for integration of exponential function, if we integrate e raised to u du, that will just be e raised to u plus c. Okay, also we can apply here integration yielding to logarithmic function. So if we have here integral of du over u, that will just be ln u plus c. Also, we can use integration by parts. So as you can recall, integration by parts will just be equal to uv minus integral of v du. Okay, and also for integral of sine u du, that will just be negative cosine u plus c. Okay, the integral of cosine u du will just be sine u plus c. Okay, and for integration yielding to inverse trigonometric functions, we are going to apply this. No, so if this is integral of du over u squared plus a squared, so that will just be 1 over a arctangent of u over a plus c. Okay, so we will also apply definite integral here. Okay, so for this integral, we have here limits, no, from a to b. Okay, so if we integrate f of x, let's say that is f of x, so we will evaluate this further from a to b. So we will just substitute the lower limit, the upper limit first, no, to all the variable, let's say variable x, so that will be f of b, no, wherein the variables x here are substituted by upper limit b, and minus, no, we are going to substitute the lower limit to all the variable x for that same function, no, and we will subtract that from f of b, no. So the answer here will be definite, okay. So also we will use the concept for improper integral here. So for proper integral, one of the limits here is infinity. Okay, so we are going to use this, that to solve for this improper integral, this will be equal to the limit of f of x dx from 0 to a, okay, wherein a approaches to infinity. So we are going to use all of this, no, in solving for Laplace transform. So we will also use some rules for infinity here in solving for Laplace transform. So let us recall some rules for infinity. Okay, so the first one is this. So e raised to negative infinity is equal to 0. So you have to remember this, that e raised to negative infinity is equal to 0. So you can actually try that in your calculator, that if you raise e, okay, to a negative large number, let's say e raised to negative 99999999999, so that is infinity. Okay, so you can see that is equal to 0. Okay, also for e raised to 0, that is apparently equal to 1. So as we know, any number raised to 0 is actually equal to 1. Okay, so you have to remember this, and e raised to positive infinity, that is undefined. Okay, so we will use these rules. Okay, so you have to remember these rules for infinity. So we will solve some calculus problems here, okay, so that we can recall the rules for calculus. No? So for number 1, this is integral of e raised to 2x dx. So this is integration. Okay, so this is exponential function. Okay, so we will use our rule for integration of exponential function. That will just be e raised to u du is equal to eu plus c. So this 2x, okay, we will have to convert it into u. Okay, we have to convert it to u first. No? So we will let u is equal to 2x. Okay, and we are going to differentiate u. Both sides, no, we will differentiate u and 2x. So that will be du is equal to 2 dx. Okay, and we are going to solve for dx. Okay, and dx will be equal to 1/2 du. So we will substitute this dx, okay, to the dx in the given, no, and we will substitute u, okay, in place of 2x here, so that it will become u, no, and from that we can apply this rule for integration of exponential function. So substituting um, 2x, okay, substituting u for 2x and substituting 1/2 du for dx. So e raised to u, which is 2x, will become u, and dx will become 1/2 du. So this will become 1/2. So we can just factor that out, no, times integral of e raised to u du. So from here we can already apply this, no. So from here, as we can see, integral of eu du will just be e raised to u plus c. So this will just become 1/2 e raised to u plus 1/2 c. But 1/2 c will just be equal to c lang din. So that will just be c. Okay, so this will now become the um, answer, no? So we will substitute u. Okay, we will substitute back. Okay, the 2x here, so in place of u, so this will become 1/2 e raised to 2x plus c. So if the given function here is in terms of x, of course your answer should also be in terms of x. So we have to substitute back 2x here. Okay, so this will now be the answer, okay, for the integration of e raised to 2x dx. Okay, for this, no, we can actually solve this by shortcut, no. So it's not necessary that you show here that you let u is equal to 2x, no. So from here, no, since you see that there is a coefficient, okay, for the variable x here, so we can just multiply, okay, the integration here, the answer for this integration, we will just multiply by the reciprocal of that coefficient. So if this is 2, its reciprocal is 1/2. So we will just multiply e raised to x plus c by 1/2, 2x plus c by 1/2. No, so we can use that as a shortcut for this, instead of showing this that you let u is equal to 2x. So you can directly multiply e raised to 2x plus c by the reciprocal of 2, since that is the coefficient of variable x. So that will be 1/2 e raised to 2x. So let's say you have here e raised to 3x, the integral of e raised to 3x dx. So that will just be 1/3 e raised to 3x plus c. So we can use that shortcut, no? Okay, for solving um, the integral of exponential functions. Okay, so for number 2, okay, so this is integral of x sine x dx. Okay, so for integral of x sine x dx, so as we can recall from our integral calculus, we can use integration by parts. okay, to solve this, since this is composed of two functions, one algebraic function and one trigonometric function. So we can use integration by parts. Okay, so using integration by parts, our rule here, okay, we will assign a function, okay, to variable u, and we will assign a function in dv. Okay, so what we're going to assign for u, okay, so we are going to use liate here, okay, to know what function we are going to assign in u. Okay, so we will use liate. So liate, this is an acronym. L stands for logarithmic function. I stands for inverse trigonometric functions. A stands for algebraic functions. T stands for trigonometric functions, and E stands for exponential functions. So this is the hierarchy, okay, of the function that we should assign to u, no, to variable u, no. So here, what function comes first will be assigned here. So for our given, no, so this is x sine x, so this is algebraic and trigonometric. So using liate, we can see that algebraic here comes first before trigonometric function. So meaning to say, we are going to assign the algebraic function of the given to u, no. So u will be equal to x here, so that is the algebraic function in the given, no, and we will assign the remaining function to dv, no, including dx, no. So the dv will be sine x dx, no. So from here, we are going to differentiate u is equal to x, and we are going to integrate dv is equal to sine x dx. So differentiating u is equal to x, this will just be du is equal to dx, and integrating dv both sides, we will integrate that. So the integral sign here and d will just be cancelled. So what will remain here is v, and the integral of sine x dx is actually negative cosine x. Okay, so from here, we are going to apply our formula for integration by parts. So that will be uv minus integral of b du. So the integral of x sine x dx will just be equal to, again, we are going to apply uv minus integral of v du. So our u here is x. So we will write x here, and our v, okay, is negative cosine x. That's why it will become negative x cosine x minus integral of v. Our v here is negative cosine x, and our du here is dx. Okay, so from here, now we can simplify this further. So negative x cosine x plus integral of cosine x dx, that is actually sine x plus c. So from here, now, this is already the answer for the integral of x sine x dx. This is equal to negative x cosine x plus sine x plus c. So this will now be the answer. Okay, now for our third example, this is integral of x dx from 0 to 2. So this is actually a definite integral since we have limits here from 0 to 2. So we will apply our knowledge here for definite integral, and for this, no, for this given, we will apply power rule. Okay, so these are the rules that we're going to apply here. Okay, so integrating this, so the integral of x dx, okay, it will just, we will just apply power rule, so that will just be x squared over 2. That's why it became 1/2 x squared here. And we will evaluate this from 0 to 2. So those are the limits, no? And using the concept for definite integral, we are just going to substitute, okay, the upper limit to the variable x minus, we're going to substitute the lower limit to the same function. Okay, so substituting these limits to our function, so this will be 1/2 2 squared minus, okay, 1/2, so we substitute the lower limit, which is 0 to x, so that will be 0 squared. So simplifying this, no, so this will just be 1/2 of 4 minus 0. So 1/2 of 4 is 2. So this will now be the answer for this. We will now proceed to solving sample problems for Laplace transform. Okay, so the first sample problem here, if f of t is equal to 1, find f of s. So the given f of t here is constant. So if this is a constant, no, so this is also a time variable function, if this is a constant, no. So if f of t is equal to 1, we are going to solve for f of s or its Laplace transform. So to solve this, we are going to use our formula. okay, to solve for Laplace transform. So this will be Laplace transform is equal to the Laplace transform of the given f of t or time domain function, that is f of t, is equal to integral of e raised to negative st ft times dt from 0 to infinity. So we are just going to substitute the given f of t here, okay, and here. Okay, so substituting that, no, so this will just be f of s equal to the Laplace transform of the given f of t, which is 1, is equal to integral of e raised to negative st times 1, so that is the given f of t, dt from 0 to infinity. So as we can see here, we are going to integrate e raised to negative st times 1 dt from 0 to infinity. Okay, we're going to integrate that. And as we can see here, this is an improper integral. Okay, so as we can recall, improper integral, it is a definite integral that has either or both limits infinite. Okay, so as we can see in this integration, one of the limits here is infinity, no? So this is actually an improper integral. And to solve for improper integral, okay, so we are going to use a limit, no? So to solve for the integral of this, which is equal to f of s, so that will be equal to the limit, okay, of the integral of e raised to negative st times 1 dt from 0 to t, okay, wherein t approaches to infinity. So we just substitute that instead of infinity here, we substitute capital letter T here. Okay, and this capital letter T, this is approaching to infinity. Okay, so to solve this, we will integrate first this, no, and then we are going to solve for its limit. Okay, so integrating this, okay, so as we can see here, the variable here is t. Okay, so we will integrate this, okay, with respect to variable t. So meaning to say, variables other than variable t here, okay, is constant. Okay, so meaning to say this s, okay, this variable s here, this is actually a constant. Okay, so we will treat s here as constant. Okay, so this will just be e raised to negative st times dt, since this is just multiplied by 1. So the integral of e raised to negative st dt, as we have discussed from the previous slides, okay, in integrating for exponential functions, that will just be e raised to negative st, okay, plus c, but we will not include c here since this is a definite integral, and we will just multiply that, okay, to the reciprocal of the coefficient, okay, of the variable. Okay, the variable here is t, so the coefficient here is negative s. So the reciprocal of negative s is negative 1 over s. So we will just multiply that, no, to e raised to negative st. So this will now be the integration of this, no, and we will integrate this or evaluate this from 0 to t. Okay, so these are the given limits here. Okay, so we will apply the rule for definite integral, that we will substitute the upper limit, okay, to all the variable t here, okay, and we will substitute also the lower limit to the variable t here, and we will subtract that, no, from the first function, no, where we substituted upper limit t. Okay, so for this, evaluating this further, okay, so we will substitute the upper limit first. So this will become negative 1 over s, e raised to negative s. So t, we substitute capital letter T here, minus, okay, now we are going to substitute the lower limit to variable t. Okay, so this will be negative 1 over s, e raised to negative s, and the t here is 0, no? So evaluating this, okay, so as we know, this t, okay, this is actually approaching to infinity. Okay, so this is approaching to infinity. So we can say that e raised to negative s times infinity, we can say that that is e raised to negative infinity. Okay, and recalling the rules for infinity, as we know, e raised to negative infinity or approaching to infinity, negative infinity, that is actually equal to 0. Okay, so we will use that here. So e raised to negative s times capital letter T is equal to 0. So this will be 0 here. And for e raised to negative s times 0, that will be e raised to 0 rather. And we know that e raised to 0 is actually 1, right? So we will substitute 1 here. Okay, so this will become negative 1 over s times 1. So negative 1 over s will just be 0. Okay, while this will be multiplied, negative times negative will be positive. So that will become positive 1 over s. Okay, so that will now be, okay, the value for this, no, for evaluating this, so that will be 1 over s. So this will now be the answer, no, for the Laplace transform of f of t is equal to 1. So this is the Laplace transform of 1. Okay, and this will only be applicable for s is wherein s is greater than 0. Okay, tama, no? Greater than 0. Okay, so it cannot be 0. Okay, because if it is 0, it will become ano, no, undefined na. Okay, so this will now be the answer, no, for this. But here, okay, so this is the proper way, okay, in solving for improper integral. But in our succeeding solutions, okay, we will directly substitute or we will directly use infinity here, that instead of solving first for the limit of this integral, okay, we will directly use e raised to negative s infinity, okay, in our calculation, no? So but then, this is the proper way of solving for improper integral. For number 2, the given here is f of t is equal to t, and we're going to find for its f of s, or for its Laplace transform. So this is the time variable function given here, and this is equal to t. Okay, so to solve this, we're going to use our formula that for f of s, that will just be equal to the Laplace transform of the given f of t is equal to the integral of e raised to negative st f of t dt from 0 to infinity. So we will just substitute f of t, the given f of t here and here. Okay, so f of t again, that is t. Okay, and for this, we will also substitute t here. So from here, we are going to integrate this, no? So we are going to integrate this, so using integration by parts. So we will directly integrate this, no? So we will no longer use what we have used from example number 1. So I just showed you there, okay, how to solve for improper integrals properly, no? But we can also solve this directly this way. Okay, so using integration by parts to solve this integration, okay, so integration by parts, again, we will assign u and dv here. Okay, and what we're going to assign to u, to variable u here, is the function that comes first in Liate. Okay, so for this integration, or this given, okay, so this is a combination of exponential. Okay, the exponential here is e raised to negative st, and algebraic. So the algebraic here is the variable t. So what comes first here is the trigonometric, algebraic and exponential. So algebraic, so we will assign the algebraic function t to u. So that will be u is equal to t, and the other function will be assigned to dv. So dv is equal to e raised to negative st, including the dt, ha? Okay, it will always be included for the function that we assign here in dv. Okay, so for this, no, we will differentiate u is equal to t. So differentiating u is equal to t, that will just be du is equal to dt. Now for dv, we will integrate this both sides. Okay, so integrating dv is equal to integral of negative e raised to negative st dt. Okay, so the integral sign here and d will just be cancelled. So this will just be v, and the integral of e raised to negative st dt, so that will just be negative 1 over s times e raised to negative st. Okay, so from here, we can now apply the formula for integration by parts. That will just be uv minus integral of v du. Okay, so applying that, so from our given here, so this is f of s equal to our u here. Our u here is t, so that will be t. And our v here is negative 1 over s e raised to negative st. So we just substitute that. uv minus. Okay, so there is a limit here, ha? So we are going to evaluate this from 0 to infinity. Minus the integral of v du. Our v here is negative 1 over s e raised to negative st. And our du here, okay, from here is dt. So we just substitute that. No, so simplifying this further, okay, so this will just be this will just be negative t over s times e raised to negative st. So we will evaluate this from 0 to infinity. And this will just become positive negative times negative, so that will be positive of integral of 1 over s e raised to negative st dt from 0 to infinity. So integrating that, so that will just be 1 over s times the reciprocal of the coefficient of this variable t, which is negative 1 over s. So the reciprocal is negative 1 over s. Okay, so we will multiply that and then e raised to negative st. Okay, so this will now be the integral or the integration of this. No? So we will evaluate this from 0 to infinity as well. So simplifying this further, so this is already simplified. We will simplify this further. So this will become negative 1 over s squared times e raised to negative st. And we will evaluate this from 0 to infinity. So we will substitute our limits here, the infinity and 0, to variable t. Okay, so we will substitute that. So we have here variable t here. So this will be substituted by infinity. And then e raised to negative s. So this variable t will also be substituted by infinity. Minus, okay, we will substitute naman ngayon, okay, yung lower limit. So that will be minus negative t. Our t is 0 over s minus times e raised to negative s times t, which is 0. Okay, so from here, minus. So we will just factor out the negative here. And we will substitute infinity and 0 to variable t here in this function. So we just factor out negative here. So 1 over s squared times e raised to negative s. Our t here is infinity. Minus 1 over s squared e raised to negative s. We substitute 0 to t. No? So that will be 0 here. No? So simplifying this further, okay, so evaluating this, as we can see here, e raised to negative infinity, this will become e raised to negative infinity, and as we know, that will be equal to 0, right? And also, we already know that e raised to negative, or e raised to 0 rather, e raised to 0, that is actually equal to 1, but there is a 0 here, so it will just become 0. Now here, this will become e raised to negative infinity, so this will become 0. Okay, and here e raised to 0, this will be equal to 1, right? So from here, okay, from here, this will become 0, this will just become 0, this will just become 0, and what will remain here is just this. Now, so this will be negative times negative, so that will become positive 1 over s squared. Okay, so this will now be the Laplace transform of time variable function equal to t. Okay, so this is already the Laplace transform of t. Okay, and this will just be applicable, no, for s that is greater than 0. Okay, so it cannot be 0 because if this is 0, this will become undefined. Okay, so this is already the Laplace transform of t, that is 1 over s squared. Okay, so for sample problem number 3, if f of t is equal to e raised to at, find f of s. Okay, so the given f of t here is e raised to at. So to solve for its Laplace transform, we just substitute the given f of t here and here. Okay, so substituting that, so that will just become integral of e raised to negative st times e raised to at dt from 0 to infinity. Okay, so evaluating this, solving this, okay, so we can apply the rule for or law for exponent, no? Since we have here the same base, e and e, so we can just add their exponents. Okay, so we can combine these two functions, no? Both with e as base, no? So this will just be e raised to negative st plus at. So we just add their exponents. Okay, so from here, no, we can factor out our variable t here. Okay, factoring out variable t, so this will become negative s plus a. So we will integrate this with respect to t. Okay, since this is dt, so we will integrate this with respect to t. So meaning to say, variables other than t are constants. So variable negative s and variable a here are constants here. Okay, if we integrate this. So integrating this, so we will apply our rule for integration of exponential functions. Okay, so as we know, this will just be e raised to negative s plus a t. Okay, it will just be multiplied by the reciprocal, okay, of the coefficient of variable t, which is negative s plus a. So the reciprocal of that is 1 over negative s plus a. So we just applied that. So the integral of this will just become 1 over negative s plus a times e raised to negative s plus a times t. Okay, and we will evaluate this from 0 to infinity. Okay, so for this, no, this is a definite integral, no, this is improper integral. So we will just substitute the upper limit and lower limit to all the variables t in this function, no. So we will substitute infinity first. So this will become 1 over negative s plus a times e raised to negative s plus a times t, which is infinity, minus, okay, so we will now substitute 0 to t, so that will become 1 over negative s plus a times e raised to negative s plus a. So our t here is 0. Okay, so from here we can now um, we can now evaluate this, no? So our assumption here is that negative s, or s here is greater than a. So if s is greater than a, so the value for this will become negative times infinity. So as we know, e raised to negative infinity, that is just equal to 0. Okay, and for this is negative s plus a, it will be multiplied by 0, so that will just become 0, e raised to 0, that is actually equal to 1. Okay, so simplifying this, as we know, this will just become 0 since it will be multiplied by 0, and this will be negative 1 over negative s plus a times 1. So that will just become negative 1 over negative s plus a. So simplifying this further, we can put this negative sign in the denominator, no? So this will become 1 over negative times negative s plus a. So simplifying this, so this will become 1 over s minus a. So this will be the Laplace transform of e raised to a t, that is 1 over s minus a. So this will just be true for if s is greater than a. So this will now be the answer for this. We will proceed now to sample problem number 4. If f of t is equal to cosine wt, find f of s. So we are going to solve for the Laplace transform of cosine wt. So to solve this, we are going to use this formula. Okay, and we're just going to substitute the given f of t here and here. So substituting that, so we are going to solve for the Laplace transform of cosine wt, and that will be equal to the integration of e raised to negative st cosine wt dt from 0 to infinity. So solving for this integration, okay, so as we can see here, we have here two functions, exponential and trigonometric. So we will use integration by parts here. Okay, so using integration by parts, we're going to assign functions for u and the remaining function for dv. Okay, so the function that we're going to assign here at u, okay, will depend on liate, no? So liate, whatever function comes first will be put here to u, no? So liate, so this is trigonometric and exponential. So trigonometric comes first before exponential. So we are going to assign this trigonometric function cosine wt here at u, no? So this will become u is equal to cosine wt, and the function that we're going to assign here in dv will be the remaining function, which is e raised to negative st together with dt. Okay, so what we're going to do here, we will derive u is equal to cosine wt, and we will integrate dv is equal to e raised to negative st dt. So let's derive this first. So the derivative of u will be du, and the derivative of cosine wt, we are going to use chain rule here. The derivative of cosine wt is sine wt. Okay, and the derivative of wt, so we're going to apply chain rule here. The derivative of wt, w is a constant and t will be the variable. So the derivative of wt is w, so that will be w here. By the way, the derivative of cosine wt is negative sine wt, okay, times the derivative of wt, which is w dt. Okay, so this will now be the derivative. Now for this, now we are going to integrate both sides. So this will be integral of dv is equal to integral of e raised to negative st dt. Okay, so integrating this, so the integral sign and the d here will just be cancelled. So v is equal to integral of e raised to negative st dt. So that will just be negative 1 over s times e raised to negative st. Okay, so we will just substitute these values, the values of u, du, dv, and v. We will just substitute that, okay, in our formula for integration by parts. So the formula for integration by parts is uv minus integral ng v du. So our u here is cosine wt. So that will be this, no? U. And our v, uv, our v is negative 1 over s times e raised to negative st. Okay, so we will integrate this from 0 to infinity minus integral of v. Where is our v? Our v is this, negative 1 over s e raised to negative st times du. So our du is this. So v du. So our du is negative w sine wt dt. So we will integrate this from 0 to infinity. Okay, so simplifying this, okay, so multiplying this 2, so this will be negative 1 over s e raised to negative st times cosine wt. So we just simplify this. Okay, we will evaluate this from 0 to infinity minus the integral of, so simplifying this, so this will become negative times negative, so it will be positive here. Okay, but it will still be negative here, so this will be positive w, so this is w over s times e raised to negative st times sine wt dt. So we can simplify this further. We can integrate this. No, so integrating this, w and s are constants, no? So the variable here is t, so w and s are constant. So we can just factor out w over s. Okay, so we can use IBP or integration by parts to solve for the integral of e raised to negative st sine wt dt. So again, this is integral of two functions, no, combined. So this is exponential function and trigonometric function. So we can use integration by parts. Okay, so we will assign functions for u and dv, which is the remaining function. Okay, so the function that we're going to assign here at u will depend on Liate. So again, Liate. So the trigonometric function comes first, no, in Liate before exponential function. So we're going to assign sine wt here at u. No, and for your dv, that will be the remaining function, which is e raised to negative st dt. Okay, so we will just factor out w over s here. So we will just leave that, no, that there, no. So here we're going to differentiate u is equal to sine wt. So differentiating this, so this will be du is equal to the derivative of sine wt is cosine wt. So we will derive further wt for chain rule, no? So that will be w times dt. Okay, and we are going to integrate both sides of dv and this function, no? So integrating this, so the integral sign and d will just be cancelled. So it will be v is equal to, the integral of this will just be negative 1 over s times e raised to negative st. So we are going to use these values for integration by parts. So we use integration by parts to solve this, no? So don't forget to include this in our final answer. So we will just solve first this, no, using IBP. So uv minus integral of v du. So we will use that. Okay, so continuing our solution here. So this is f of s. So we just rewrite this, no, from the previous slide. No, so we rewrite this and then we apply IBP for this. So that is uv minus integral of v du. So don't forget the w over s that we factored out. So that is negative w over s. Okay, and we will apply IBP, uv. So this is the uv, no, from the previous slide, uv minus integral of v du. So this is v du. Okay, so from here, no, we will simplify this. So simplifying this, no, so we will multiply negative w over s for this, no. So we multiply negative w over s here. So this is negative 1 over s. So that will be negative w over s times negative 1 over s. So that will be positive w over s squared e raised to negative st sine wt. So we will still evaluate this from 0 to infinity And then negative W over S times negative, so that will become positive, but this is negative here. So that will become negative here. That will remain negative here. Okay, so that will be W over S times, this will become W over S as well. So W over S times W over S, that will be W squared over S squared. Okay, and integral of e raised to negative st cosine wt dt from 0 to infinity. So from here, okay, so we can notice here, okay, at this point, okay, that the integral of e raised to negative st times cosine wt dt, this is actually, from 0 to infinity, this is actually f of s. So if you will look from the previous slide, okay, so this is actually f of s. This is equivalent to the f of s, okay, to the given f of s. Okay, so since this is f of s, okay, so we can substitute f of s for this. So this will become w squared over s squared times f of s. Okay, so this f of s, we can combine this to the f of s at the other side. So we can transpose this to the other side. So transposing it to the other side, since it is negative w squared over s squared f of s here, so if we transpose it, it will become positive. So this will become f of s plus w squared over s squared f of s equal to, okay, we just rewrite this, and then plus, we just rewrite this. Okay, so after that, no, so we can simplify this further. Okay, we can factor out f of s here. Okay, so this will become w squared over s squared plus 1 times f of s. So we just factor out f of s here. And this will be equal to, okay, so we can now start evaluating this and this from 0 to infinity. So let's evaluate this first. Okay, so this is negative 1 over s e raised to negative st cosine wt. So we will substitute first the upper limit. We will substitute infinity to all the t here. Okay, so this t will be substituted by infinity, and this t will be substituted by infinity. Minus, okay, we will substitute the lower limit here to all the variable t here. So this will become negative 1 over s e raised to negative s times 0. We substitute 0 to t here. And cosine w times 0, which is, that is the value of the t for this now, for the lower limit. So we will evaluate this, and also let's also substitute the limits here to the variables t for this. So this will be plus infinity, we substitute to t. So this will become infinity here, and for this it will become infinity as well. Minus, okay, we will now substitute the lower limit. So the t here and t here will become 0 and 0. Okay, so simplifying this further, okay, so as we know, okay, we can solve for the least common denominator of this 2. No? So this will be s squared, w squared plus s squared over s squared. So we just combine these two. Okay, so f of s equal to, okay, as we know, e raised to negative infinity will just be 0. So it will be 0 here. So it will just be 0. This entire term, no, it will just be 0. And then for this, as we know, e raised to 0, that will be 1. And then cosine of 0, so w times 0, that will become 0. So cosine of 0, that is actually 1. So you can try that in your calculator, that the cosine of 0 is 1. Okay, so for this naman, okay, e raised to negative infinity will be 0. So this whole term will be 0 lang. Okay, and then we have here w over s squared. So e raised to 0 will be 1, but sine of 0 is equal to 0. So it will just be 0 here, this entire term. So what will remain here will just be this term. Okay, so this will become negative 1 over s times negative here. So that will become positive. So that will be positive 1 over s. So solving for f of s, we are solving here for Laplace transform. How? For f of s. So to solve for f of s, we will divide both sides by w squared plus s squared over s squared. Okay, for it to be cancelled here. So it will be multiplied this way. Okay, so this will be 1 over s times s squared over w squared plus s squared. So simplifying this further, so we can cancel s here. 1 s here will be cancelled. So what will remain here is s over s squared plus w squared. So this will now be the Laplace transform, okay, of the given f of t. Okay, so we can now box this. Yun. So this is already the answer for this problem. Okay, so for the Laplace transform that we solved from our examples, okay, they are actually the derivations, okay, of some of the elementary functions, or the Laplace transform of some elementary functions. So we already derived the Laplace transform of 1, and we know that that is 1 over s. We already derived the Laplace transform of f of t, and we know that that is 1 over s squared. For t raised to n, so we did not derive this, but its Laplace transform is n factorial over s raised to n plus 1. For e raised to at, we derived this also, and we know that its Laplace transform is 1 over s minus a. For cosine wt, so we also derived this, so the Laplace transform of cosine wt is s over s squared plus w squared. For sine wt, so this is its Laplace transform, w over s squared plus w squared. For cos wt, that will be s over s squared minus w squared. For sine hwt, that will be w over s squared minus w squared. So these are already the established Laplace transform, okay, of some elementary function. So you have to memorize this. You have to be familiarized with these Laplace transforms, no? Because we are going to use this in our succeeding topics, no? So instead of deriving them, okay, when we solve the Laplace transforms, no? So we will directly use them. So it will be very important that you memorize this, no? Okay. So that concludes our discussion. I hope that you learned, but don't just go yet because I am giving additional points. Okay, so I will give additional points, bonus points for those students who will comment their name, their section, and the concept that they learn, okay, from this discussion. So you have to comment that in the comment section, and the first five students who will comment, okay, will receive the bonus points. I hope that you see this. Okay, so for bonus points, okay, sana makita mo ito, class. Ayan, so that's all. Thank you, class, and keep safe. God bless. Bye-bye.